In this video, I'm going to talk about the electromagnetic wave equation. And we're going to somehow derive this equation in a simple case using the four basic equations that lay the foundations of all electric, magnetic, and optical phenomena. These equations, I would write them explicitly in differential form and in the international system of units, namely known as the SI units. These are the infamous Maxwell's equations. The first of these equations states that the divergence of the displacement vector gives, or let's say it is derived by the source of electric charge. The divergence of the magnetic induction is zero. The curl of the electric field is given by the negative time derivative of the magnetic induction. And finally, the curl of the magnetic field is given by the current density, free current density, plus the time derivative of the displacement vector. These four equations are known as Maxwell's equations. Each of these equations has its own history. In fact, the theory of electromagnetism was, scientifically and accurately developed in the 18th and 19th century. There have been multiple figures that contributed to the development of these equations, starting from Coulomb and then through the works of Ampere, Faraday, Maxwell himself, and many, many other great scientists and mathematicians. They actually piece by piece formed these four equations as we know them today. And the remarkable fact is that each of these equations written in this differential form are first order partial differential equations. And they are, as I said, the foundations of our modern understanding of classical electrodynamics. I'm not going to discuss in detail what each of these equations tell us. They are all based on experimental facts. They are all independent of each other, meaning that one of these equations cannot be, any of these equations to be exact, cannot be driven or found by other equations. So they are completely independent equations, but they all form this neat, compact package all together. The first equation is Coulomb's law. You're familiar with it. It's a differential form of Coulomb's law and Gauss's law. The second equation gives us the experimental fact that there are no observed magnetic monopoles in nature. The third equation is attributed to Faraday, Michael Faraday, which he showed us that spatial variations in the electric field is given by the temporal variations of the magnetic induction. This minus sign is attributed to Lenz, who made a correction to Faraday's equation. The third equation, in fact, which is called Faraday's law of induction, by the way, was actually telling that there is an interconnection between electric fields and magnetic fields. So the spatial variations of the electric field can be given by the temporal variations of a magnetic field. So the changes in the magnetic induction here, to be exact, derives what we call the electric field. The fourth equation is sort of a mirror image of this third equation. And this is the equation that we know it as the Ampere Maxwell equation, this fourth term, which gives the time variations of the electric displacement vector was introduced by Maxwell himself, we would see that this is an essential term that is needed in order to understand the generation and propagation of electromagnetic waves. As a particular example, the propagation of light waves. And this first term, of course, is the source of the magnetic field that is shown by H. It's the electric current density. So in order to keep things simple, what I'm going to do is I'm going to consider first let's define what these fields and these sources are. D is called the displacement vector, or the electric displacement vector. B is called the magnetic induction. E is called the electric field. H is called the magnetic field or the magnetic intensity, some call it. These are the four fields. In general, all of them are functions of space and time. So maybe I should show it this way. D is a function of space and time. Likewise, B is in general a function of space and time. E is a function of space and time. And H is a function of space and time. D and B are sometimes called the responses to E and H. What I mean by that is if I consider linear media, there's a linear relation between dB and E and H. D can be given as a scalar factor epsilon times E. Epsilon is called the permittivity of the medium. And B, magnetic induction, can be given as a factor which we call mu, which is called the permeability of the medium, the magnetic permeability of the medium times the magnetic field. If I look into free space, where as free space, what I mean is a medium that has no magnetic or electric properties, then the displacement vector is simply the electric field multiplied by a constant factor, which we call epsilon naught, and that is called the permittivity of free space. And the magnetic field or the magnetic induction is just simply a constant multiple of the magnetic field. This mu naught here is called the permeability of free space. The numerical values of epsilon naught and mu naught and SI units are given as 8.85 times 10 to the minus 12 in some units. Right now, we don't really need to worry about the units. And for the magnetic permeability, that is also given as 4 pi times 10 to the minus 7 in SI units. All right, so in free space, the displacement vector and the magnetic induction take these forms. On the other hand, looking back into Maxwell's equations, we see two terms here, or two, let's say, sources, rho, and in this case, rho F, which is F stands for free. It's called the charge density. It's the electronic charge density. And this little subscript F, we put it to indicate that we're not talking about bound charges, we're talking about free charges. And the J in the fourth equation is a vector which we call the current, the electric current density. Again, that F stands for free. It's a free current density. I'm not talking about bound currents. So these two terms here are the sources of my fields. Sources other than the fields themselves, okay? Because the third and fourth equation tell us that the fields themselves can produce or can be treated as sources of E and H. Now, if we consider free space, or let's say vacuum, in a region in which there are no um, sources of charge and current, then in that case, the four Maxwell equations would take this simple form. The first equation would give the divergence of E to be zero. The second equation gives us the divergence of H to be zero. The third equation would result in this form. That would give the curl of E as minus mu naught times the partial time derivative of the magnetic field. And finally, the fourth equation would give the curl of the magnetic field as epsilon naught times the partial derivative of the electric field. If you want to know where these come from, it's very simple. All you have to do is, in the original Maxwell equations, let D be epsilon naught E and B be mu naught H, and consider rho and J to be zero. And in that case, you can easily find the form in vacuum or in free space. Maybe I should just write it down so that you can see how it works. So let's say we're talking about free space. So divergence of D, let's say the original form is rho F. So if I'm talking about a region where there's no charge density, and we're talking about a linear medium in which the by the way, this epsilon, sometimes people call it the dielectric constant. The permittivity is that of the permittivity of free space, and this would easily look like the divergence of epsilon naught E equals zero. And since epsilon naught is a constant, it can come out of the divergence operator. Write it as epsilon naught times divergence of E equals zero. And divergence at epsilon naught, although in SI units is a very tiny number, but it's other than zero. So that leaves us with the divergence of E being zero. That gives us the first equation. The second equation, which is about the magnetic induction, originally it was in this form. Again, in a region in which, let's say, the magnetic so if there's no source, obviously the second equation doesn't involve a source, but in outer space and free space or in vacuum, the permeability can be replaced by that of free space. And in this way, I can write this second equation as the divergence of mu naught H, that being zero, again, mu naught being a constant. It's mu naught times divergence of H is zero, and it is a non-zero constant. As you can see, here's 4 pi times 10 to the minus 7. So that leads us to this equation. The divergence of H is zero. That gives us the second equation. The third equation, again, can be worked out starting from Faraday's law of electromagnetic induction. Curl of E is minus partial time derivative of the magnetic induction. Again, in a region that we don't have any source and it's a linear region in free space, B is mu naught H simply, so I can write the curl of my electric field to be minus time derivative of mu naught times the magnetic field. Mu naught is a constant. I can come behind the partial derivative operator, and we end up with curl of E be minus mu naught times the partial time derivative of the magnetic field. That gives us the third equation. And finally, for the fourth equation in vacuum, I'm going to start with the original equation, which is written in this form. We can easily work our way out by considering the fact that D is epsilon naught E in free space, and J is zero. There are no current densities, even if there's an absence of of electric currents. In that case, then this curl of H would simply give us the time derivative of epsilon naught times E. I can bring that epsilon naught as it's a constant, put it in front of the time operator, and write this as the curl of H equals epsilon naught times the partial time derivative of the electric field, which gives me this equation. Okay, so in vacuum and in the absence of sources, Maxwell's equations give me this. Okay, now I'll start with these equations, and I will use vector analysis in order to find the electromagnetic wave equation. Now, the way we're going to do that is I'm going to take the curl of both sides of the third equation. So if I look into the third equation and I take the curl of E, that would give me the curl of minus mu naught times the time derivative of my magnetic field. Now the left-hand side can be simplified or can be written by the back cab rule in vector analysis. So in a separate video, I will show you how this can be done. This simply gives me the gradient of the divergence of E minus the vector Laplacian of E. The right-hand side, on the other hand, you can see that this minus mu naught is a constant. It can come outside the curl operator, and we are left with the curl of the partial time derivative of the magnetic field. All right, let's see if we can simplify this even further. Here we have the gradient of the divergence of E, but earlier we saw that in a sourceless medium, the divergence of E is 0. So here, the first term is just 0. And I can cross out these minuses and come up with a form like this. The Laplacian, the vector Laplacian of my electric field would be given as mu naught times the curl of the time derivative of my magnetic field. Now, in classical electrodynamics, space and time are independent entities. Okay, we're not talking about the space-time continuum. We're not talking about the relativistic cases. So in classical physics and classical electrodynamics, space and time are independent. So the operators of space and the operators of time can be interchanged, right? They don't depend on each other. So I can take this term here and write it as the time derivative. Second, I can write it as the time derivative of curl of H. Easily interchange the order of these differential operators, because as I said, space and time are independent here. So therefore, at the end of the day, Faraday's induction gives me an equation like this: mu naught times the partial time derivative of curl of H. But I'm not done here yet, because I can also realize that this curl of H that is appearing here can be given through Maxwell's fourth equation as epsilon naught times the time derivative of the electric field. So I'll just simply replace that. I'll write this in this form. The Laplacian of the electric field would give me mu naught times the partial time derivative. And instead of curl of H, I'll substitute what it is. It was epsilon naught times the time derivative of the electric field. And again, since epsilon naught is a constant, it can come out of the the derivatives with respect to time operator, and I'll write it in this form. The Laplacian of the electric field is epsilon naught mu naught times the derivative of the derivative, the second order derivative of the electric field with respect to time. And if I look into this equation carefully, this actually is the mathematical form of a wave equation, right, that actually propagates with a fixed velocity. Now, what is that velocity? In general, let's say in one dimensions, for instance, in one dimensions, the wave equation of, let's say, a function of space and time, let's call it f, has this mathematical structure. We just say the second derivative of f with respect to position minus 1 over v squared times the second derivative of f with respect to time. It's right here. That is 0. Okay, this is the form of a one-dimensional wave, right? And here v is the speed of the wave. So any multivariable function that satisfies this equation is a wave. Now, if I compare this one-dimensional wave equation with this three-dimensional form here, I can just simply see that I have three components for my gradient or the Laplacian operator here. I can say that, all right, this is actually giving me a wave with a speed of 1 over epsilon naught mu naught to the power 1/2, right? It's easy to see. I can just take this here and bring everything to the left-hand side. And if I consider or compare this with this, I can find that easily see that the reciprocal of the square of the speed of my wave is epsilon naught mu naught. So let's see what that is. So change the color here because this is an important part here. You can see that 1 over the speed of the wave is epsilon naught mu naught, okay? If I were to calculate this in SI units, I would end up with 1, let's say, over the square root of epsilon naught mu naught. Plug in the numbers, 1 over the square root of 8.85 times 10 to the minus 12 times 4 pi times 10 to the minus 7. And it is remarkable that this turns out to be 3 times 10 to the 8 meters per second. And what is this? Well, there's only one wave that moves at this velocity or this speed in nature, and that is called light. So this is the speed of light. Which we show by c. So you can say that this actually gives us this identity here, that epsilon naught mu naught c squared. So it's going to be 1. And in that case, my wave equation is now written in this beautiful, simple form. Sometimes in some literature, we take the vector Laplacian operator minus 1 over c squared and the second time derivative operator. We put them all in one package and define a new operator, which is called the D'Alembert operator here. So we show it with a square. So at the end of the day, my electromagnetic wave equation is given by this simple 1-inch line. So let me zoom out a little bit to show you what's been going on here. So here we started off with Maxwell's equations here, and then we simplified for the case of a region that lacks charge and current density, a linear media, namely vacuum. And we played with the third equation, like Faraday's equation, took the curl of both sides, and we used the fact that time and space are independent quantities in classical physics. And we ended up with something like this equation here. And we used the fourth equation, which is Maxwell's equation, or the Ampere-Maxwell's equation, and replaced the curl of H with the time variations of the electric field, and we ended up with this. In other words, given the fact that Maxwell introduced this term into the equations, before him, we weren't aware of this term, and thereby we couldn't, realize propagating electromagnetic fields. Now, with the aid of Maxwell, we can actually find that the electric field satisfies this equation here. So with this simple derivation, I just showed you that the electric fields are propagating in vacuum with a tremendous speed, which is the speed of light, 3 × 10⁸ meters per second. You can do a similar calculation and show that the magnetic field would also travel with the speed of light in the same way. All you have to do is to take the curl of the fourth equation and then simply replace let's say curl of E by Faraday's law in terms of the magnetic field, and then you would end up with exactly the same equation that we ended up for electric fields. So that can be a separate exercise that you can show for yourself. So the magnetic field in vacuum also satisfies the wave equation. So I hope you've learned how to derive the electromagnetic wave equation using Maxwell's equations. And you can see that classical electrodynamics, when it's formulated in the language of vector analysis and differential vectors, it turns out to be very simple and very easy to handle. That's why knowing vector techniques and vector analysis is essential to get a simple and firm understanding of what goes on. Of course, we've solved this problem for a simple scenario for a case of free space and vacuum. Obviously, if we're talking about material, if we're talking about how waves propagate in matter, then we would have to, consider the fact that the responses, E and B, will first of all not always be linear. There are nonlinear media as well as linear media. And the second thing is that we have to look on how the permittivity and the permeability depend on the characters of the medium. And all of these different scenarios, different problems can also be worked out using vector analysis. Anyway, if you find this video useful, please share it with your friends and colleagues. If you have any questions, leave it in the comment section. And until next time, take care of yourselves. Bye-bye.